Hi, my name is Ivar Pedersen and I'm a PhD candidate in the BRU21 program. The title of my PhD project is Industry 4.0 and Smart Predictive Maintenance. When it comes to specific application of Industry 4.0, predictive maintenance is often one of the first to be mentioned. And by predictive maintenance, we mean a maintenance policy where we track the degradation of an item over time and we use a model to estimate the remaining useful time of that item. And by that we mean the time before the degradation reached the defined failure threshold. I will now give you an example of how predictive maintenance can be done, and that example is based on a paper presented at this year's SFL conference. And the title of the paper is Degradation Modeling of Centrifugal Pumps as Input Predictive Maintenance. And the full paper can be found at the SFL homepage. So in this paper, we used a health indicator called head deviation, where we look on the deviation between the expected head or the pressure out of the pump based on the pump curve from the manufacturer and the actual head from the pump based on the sensor data. And by tracking that health indicator over time, we saw that there was gradual degradation happening to the pump. And when we changed the impeller of the pump, it went back down to zero and started degrading again. So this told us that this was a good indicator for the state of the impeller of the pumps. By closer examination of several degradation paths, we decided to use the Wiener process to model the degradation of these pumps. And a nice thing about the Wiener process is that then the first passage time of the defined failure threshold is inverse Gaussian distributed. This is a property we can use to make our rule predictions or the predictions of the remaining useful life. So here we have one degradation path from the test data set. And we see the health starts at around 0, and then the health indicator goes all the way to 10, which is the defined failure threshold, at around operating day 120. This is the actual remaining useful life of that pump. At operating time 0, it is 120 days left of the pump. It goes down to 0 when the pump reaches the defined failure threshold. The green line is our median estimate for remaining useful life based on our model. As you can see, the fit is quite nice with the actual remaining useful life, but because it's often much more expensive to do maintenance too late than too early, it's normally wise to use a more conservative estimate for our rule prediction. Our conservative estimate here is the 10th percentile of the rule prediction. This is useful information because we can use this estimate of the remaining useful life to make our maintenance decision. So say, for instance, that we have 10 days mobilization time for mobilizing for our maintenance. And if we want to mobilize for maintenance as late as possible, but still be fairly confident that we don't mobilize for maintenance too late, you have to mobilize at around day 70. But as you all can see, the gap between this conservative estimate and actual rule is quite high, and in the remainder of my PhD project, I will expand on the classic Wiener process to make this gap smaller. My PhD project is sponsored by NTNU. Thank you for your attention.